Okay, before I go on to examples 1 and 2, I want to deal with Euler's notation for imaginary numbers. Here's what he invented. He invented the letter I to represent this exact thing, the square root of negative 1. And the square root of negative 1 does not exist. It's not possible to have a square root of negative 1. Here's why. If I do 1 times 1, what do I get?
1.
And if I do negative 1 times negative 1, what do I get?
1.
1. I can't multiply a number by itself to get a negative number, a negative 1 in this case. But if I do I times I, that's going to equal negative 1. I is the magical number that if you multiply by itself, you get a negative 1. All right? As you can see down here, I to the first is I squared is negative 1. If you do I squared times I, you're going to get negative 1 times I, which is negative I. If you do I to the fourth, which is just I squared times itself, which makes positive 1. Then I to the fifth would be I to the fourth times I, gets back to I, and then it just repeats itself. It's a repeatable pattern. And it's very, very easy to memorize this. You memorize this little sentence here. I won. I won. Imagine you just won a game. I won, right? I won. Just remember the minuses are in the middle. And then you got your pattern memorized. So this is the magical mnemonic device that helps you memorize that. Just make sure that the negatives are in the middle. I won. So.
And they don't ever equal. They're always going to be 1 and I.
If you're just dealing with i's, then yes, you're going to get 1s and negative 1s, and i's and negative i's.
Okay.
If you start putting numbers times it, like 5i times I, that makes a negative 5. Because I times I makes negative 1 times 5 makes negative 5. So if there's numbers involved beyond the i's, figure out the I is first, and then deal with the number second. And the last 2 examples are going to deal with that. Actually, the last 3 examples deal with that stuff. So let's take a look at example 1. I'm going to show you a rule that you learned back in Algebra 1, and you guys did it all the time, and you're really good at it, and you didn't pay attention to the first part of it.
And we didn't?
No, you didn't. Nobody ever does.
Oh, okay.
If A is greater than 0 and B is greater than 0, then the square root of A times the square root of B is equal to the square root of AB. That's the rule. Everybody pays attention to that, but nobody pays attention to that. All right, focus on this. Part A, notice the numbers underneath the radicals are positive. The rule says to multiply the square root of 2 times the square root of 3, I'm simply going to get the square root of 6, right? Because I can use this rule for that problem because both the radicands, A and B, 3 and 2 in this case, are positive numbers, so we're allowed to use that. I am not allowed to use this rule on the second or third problem because even though this is positive, this isn't. Neither one of these is positive. All right? So let me just caution you right away. This is a rule I've used a lot. Just recently we used it on these square root of 2/7 type problems, right? We multiply top and bottom by the square root of 7. That gets me the square root of 14 on top. We get the 7 on the bottom, right? We've seen these? And we just do that blindly at this point. We just know it works, so it works, let's just do it. But again, the requirement of the rule is that the radicands must be positive. Now they're not going to be positive all the time. Now we're going to get some negative radicands occasionally. So the way we deal with this, because I want to use that rule, but I can't, is I need to rewrite this so that these numbers are both positive numbers. And the way we do that, any minus inside a radical becomes an I. And let me show you how that happens so that we can understand. Negative 1 times 2 is the same as negative 2, right? And anytime I have a number inside a square root that has an exact square root, I'm allowed to take it out, right? We just found out on the last page, because our friend Leonard Euler said it, that the square root of negative 1 equals I, right? So, wrong way. So that equals I. The square root of 2 doesn't have a square root, so it stays in. But notice, once I do that, that gets me to a point where, drop my pen, these numbers are both positive now, so now both numbers are positive, so I'm allowed to use the rule, right? So again, I can't use the rule in the current state, but I can change the structure so now I can use the rule. The square root of 6 gets to be the square root of 6. The I is part of the answer. You're welcome to put it right there in front. You could also put the square root of 6I. Just be careful the square root sign stops. The I is not underneath the bar. Okay? That means this right here is geotrig level stuff, and we're not doing that this year. That's next year, unless you're a person who's taking both classes, in which case you can do it this year. Chapter 7. The last problem, same issue. Both numbers are negative, right? So first thing I need to deal with is this is the square root of negative 3, which is I times the square root of 3. And this is the square root of negative 2, which is I times the square root of 2. And at this point, once I get them both to positive radicands, the 2 and the 3 are both positive numbers, now I'm allowed to use this rule again, so I get the square root of 6. That's going to be multiplied by I squared. What does I squared equal? Negative 1. So we're going to get negative the square root of 6 for the answer to that. And going back to what I was telling Braden earlier, this is imaginary and so is this, but when you multiply them together you get a real number. Okay, so again, sometimes real numbers exist even when imaginary numbers start off in the problem. So we want to study this topic because we have the ability to do it. We have rules to go by, and it's kind of cool to be able to deal with these numbers.